So my name is Luke Powell. I'm going to go over a basic introduction on how to set up the Android environment, set up the emulator, and then get started with graphics on the Android environment using OpenGL ES2, which is the embedded systems version of OpenGL, which has a couple differences and different ways of doing things than desktop OpenGL. So beginning, our environment, a bunch of tools we're going to need. You're going to need to set up Eclipse, the Eclipse ADT, which is the Android development toolkit. That includes your emulator, all the tools to make SD cards that you can run on the emulator, everything to do with getting your devices to communicate with the Eclipse. Making everything work is for the Eclipse ADT plugin. The Android SDK, that's all the actual source code you need. So that's all the libraries, et cetera, you're going to be linking into. The Eclipse ADT, Eclipse, Android SDK all work together to make everything coherent. If you have an Android device, you can find instructions to set up that up there at that link. I generally suggest to work on a device. The emulator, you can make it work correctly. You can make it work fast, but in general, it's a bit slow and a bit buggy, and it doesn't necessarily support all the features you want to test on your device. It took 2 years for me to get OpenGL ES2 or some such odd amount of time to get that working on the emulator once it was supported on the devices. Also, your computer has no concept of you tilting it. So if you want to make something of tilting, Bluetooth, et cetera, you have to use a device to test it anyways, and it's usually faster, better to work on that device. So basic setup, once you have that, Android SDK, Eclipse, Eclipse ADT setup, we can create Android projects. File, new Android project. Not complicated if you've used any IDE before. And that's the same setup. Once the project is created, at least once you need to right-click, run as an Android project to tell it what type of project you're running it as. Also, it has no idea what it needs to run as if you're actually running it. So it's like, OK, you tell me to run an application. What is it? So first time through, right-click, tell it to run as an Android application. After that, you can hit, you use the keyboard shortcuts or hit the actual play button on the top of the screen. So emulator, it's for free. iOS, you have to pay. iOS emulator is free. Android emulator is free. And working on a device is free. So that's nice. Either way, if you pay for a device, you don't need anything extra. Emulator, if you don't have the money to pay for a device to learn Android development, that still works. Once you get into more complicated things, you're of course going to need to go get a device to actually be able to test all the full features thereof. As I said, it can be slow unless you enable hardware acceleration, graphics acceleration. Else is going to be, hey, look, I click something, wait 5 minutes, it may work. If you don't have a device, no money, emulator's fine. So create an emulator, more formally an Android virtual device. Window AVD manager. That allows you to create an AVD manager. For GPU emulation, you need to be running an AVD version 4.0.3 or above. That's when they introduced the GPU emulation and support into the Android toolkit. Was around when they were releasing Android 4.0.3. This, however, does not mean that you're developing an Android 4.0.3 application. You can develop any application less than Android 4.0.3 or equal to Android 4.0.3. That version is this of the Android virtual device itself. Nothing to do with the actual project you're running on besides it needs to be a version greater than or equal to the version you're currently developing. All versions higher than 4.0.3 also have GPU emulation supported. This actually allows you to use OpenGL ES2 on the emulator. So if you're going through and looking at the sample code, you don't have a tablet or a phone to run it on, you have to go through and enable the GPU emulation to actually support this. General hardware acceleration was from tools revision 17 and above, so that was quite a bit ago. This is hardware and operating system specific. So down there, developer using the emulator, just go to that website. It'll show you what you need to do to get all the tools you need to be able to use the hardware extensions for either Intel or AMD. So Intel is AVX, AMD has their own feature to allow hardware acceleration of virtual machines. So if you're using something like VirtualBox, you can do this to get hardware acceleration in your virtual machine. So when you're actually using this on the Android, make the emulator go fast, that means you need to actually have whatever operating system running on already installed. You're not going to be running your hardware acceleration inside of a virtual machine. That's a bit silly. So if you're on AMD, you have to work on Linux and a non-virtual machine, have to make some partition, make an entire computer for that, as you can only have hardware acceleration on AMD processors on Linux currently. If you're using an Intel processor, you can use Mac, Windows, or Linux. all the instructions for those individual operating systems are on there, and it's a bit complex to get into, but as long as your processor supports the newer hardware acceleration extensions of both AMD or Intel, this will actually make the emulator usable versus completely slow and not really usable at all for game development. So now that we have everything set up, I can show you how to get the graphics simulation up and running. That's not too difficult. So basically, once you have the Android development environment running, you have both the Android SDK manager that allows you to install new versions of the Android SDK. So if they release 4.1 and you want to develop for it, you go to the Android SDK manager. They're phasing this out in the newer tools revisions. They have some new means to do it, but that was only happening a couple days ago. AVD manager. This is where you have all your Android virtual devices. So this is where you control all your emulators. So if you create a new emulator, give it a name, give it a target. So in this case, we need at least 4.0.3 or above to use the GPU emulation. CPU, you can select between ARM, MIPS, or x86. To use the hardware acceleration, you have to be using an x86 image as you're running on an x86 processor compatible. So as long as you're running an x86 emulator image, you'll have your nice hardware acceleration. So you can go ahead and create an SD card. So if you want to, you can just give it an arbitrary size, push files on there once the emulator is running, or you can give it to an actual disk image, mount that as if it's a virtual hard drive, and put files on there that way. Down here you have hardware, so you can say this has an abstracted LCD display, so yay, something to display with. Max size for the heap, and the amount of device RAM. To actually enable GPU hardware acceleration, it's just adding enough for a hardware feature, GPU emulation. And now you have a fancy little GPU emulation set to no. Yep. Change to yes, and look, now it's actually going to run graphics properly instead of being, hey, look, you're trying to run OpenGL, I'm going to crash and cry and run away from you. Not very helpful to have your emulator running away from you in tears from you trying to get your game up and running. So that's creating the AVD. So now onto some of the actual restrictions of the Android environment. Android does not work the same manner that Windows does. There's no main. There's no singular, hey, look, I'm in main. Yay, that's good for you. Instead, there's some main somewhere in the Android system itself, but you don't have access to that, much like WinMain. Most tutorials start. So instead of having main and going, you have this activity lifecycle. So your activity is launched, then it gets called on create. That's called, hey, look, the application created itself is ready to go now. Not many places actually use on create. Most everywhere uses on start, because on start is when you actually want to set up the GUI environment. So that's where you just want to tell it, hey, look, I'm going to be bringing up OpenGL. You're going to be setting all that up in on start. On start, however, is not like main. That's called more than one time throughout your application's lifecycle. So call your application, on start is going to get called more than one time. So when you're doing logic, you want to make sure you're not assuming that on start gets called once. That's not true. On start gets called multiple times. After on start's called, on resume is called. So after that, you have activity running. If enough activity or something comes to the foreground, your activity is then paused. So when your activity is paused, you basically go, oh no, I'm going out of focus. You can free any memory or resources you're using out of the system, so you're not just taking up memory sitting there doing nothing. On resume, you can regain resources if you want to. So when the user returns back to the activity, you can resume what you want, regrab control of the volume manager, regrab whatever textures you lost. Anything you lost during on pause, recreate it on resume. You're just basically going to sit in after on pause. If something with a higher application comes through, your application will actually get killed. So there's really not too much of an immediate exit here. There's no, oh look, application's dead, everything's cleared out of memory. So if you have static variables keeping track of singletons or something, your application gets paused, comes back to on start, your global system singletons are still going to be there. Any values you set statically are still going to be there. They're still going to be set. They're not necessarily going to be cleared. However, they may be cleared if you got back to on start from the process being killed. So there's just a lot more state information you want to keep track of depending on where you are in this flow chart. Make sure everything is still going succinctly and you're not losing any data. So GUI should be created on start. So OpenGL considerations. OpenGL on the Android platform by default has its own thread. So on Android, you're kind of forced in the multi-threading of gaming. You start your application, you have your one main UI thread. This controls all the user inputs. So if the user hits the space bar, if they have a keyboard on their device, hits a touchscreen, it'll all go through the main activity on the UI thread. The UI thread can, in good practice, you should not block the UI thread, as then you're stopping all input from the user. You're just freezing up your application, and it just seems like bad application design. As you're sitting there, your application's frozen, not responding. Did it crash? Did it freeze? Or are they just not following the good principle of not freezing the UI? So freeze the UI thread, your entire UI stops responding, you don't get any input. That's bad. So OpenGL will start rendering on its own thread. So by default, it's not rendering when you tell it to. It just goes, oh, those things are dirty, or I'm ready to render now, and it'll render. You can override this to tell it to render when you want it to, or you can just leave it alone, let it render whenever it wants to. Your game, you probably only want to render when you want it to render. So basically, you can tell the render only when I tell you to. Generally a good thing to do. If you want to create textures or do any OpenGL calls, they have to be done on this thread. So all this thread management is done through a class called the GL surface view, which will in general be extending and deriving off of to implement your own functionality and adding on to it. So you can queue events to this view, and at some point it'll go, oh look, I have an event queued, I can run this now. So you can't just say, so when you're loading a game object, you want to load a texture, you basically have to tell the OpenGL view when you want to load this texture. And when it's done, that texture will be loaded. So you just have to make sure your loading is thread safe, as OpenGL wants its own thing, the UI thread wants its own thing. If you want to change what's being displayed, whether your OpenGL view or using an Android built-in view, you have to do it on the UI thread. If you want to do pop-up dialogues or UI stuff, that all has to be done on the UI thread. And if you want to actually have a game running, you can't block the UI thread. You can't really block the OpenGL thread. You have to create another thread for the game, and to make sure your game thread is happy with the OpenGL thread as far as loading goes, and is happy as using with the UI thread to get the Android UI working there, and making sure on resume and on pause are sending messages to everything that on resume and on pause needs to control. So I was just telling OpenGL, hey, look, you're paused. You can get rid of your textures or calm down for a minute, as we're not going to be rendering to you for a while. Hit that one all the way back there. So more considerations. Sometimes you want unsigned types with your OpenGL call. So let's say you're drawing something with indices. You want your indices to be unsigned, because what does negative 32,000 for an indice mean? That makes no sense at all. So what you need to do is go one size up. So if you want short indices, you need to go up to an int. If you want ints, you need to go up to a long. If you want unsigned long indices, which aren't supported, don't know why you do that, you have to go to a long. If you want long indices, you're kind of out of luck, as you're not going to go any higher, and long should hopefully be big enough for its positive signed values to be what you need. You don't go bigger than long. So what you need to do is go one data size up. So if you want to get unsigned short indices, what you basically need to do is, hey, you're an integer, and read it as an int, and then cast it back down to a short. That gets by to not having the unsigned types. That's nice and handy. So there's a couple calls where OpenGL wants unsigned ends, and that was the way you have to go around it. You're just going to say, hey, you're getting an unsigned short, pass it a signed short that you've converted down from an int, it'll work fine. It's a bit weird and a bit awkward, but that's what you have to do to get past the limitations of Java. So if you want to make sure when you have your application on the market that only devices that support OpenGL S2 can download it, there's the manifest.xml that controls everything your application needs. So it's like, hey, I want to use your internet, I want to use the alarms, I want to control your volume. Any permissions to change the device's state, or any requirements of what you want a device. Hey, you have to have a keyboard, you have to have a touch screen, which zero Android devices essentially don't have touchscreens, so that one's a bit silly. But there are still some things that don't support OpenGL's version 2. So if you tell the system that we require OpenGL ES2 with this couple lines you add to the XML file, you're all good, and only applications that can actually run OpenGL 2 will be able to run your application from the Android market. It's a good thing to make sure you're not sending out your application saying, here, install this, and it won't work on your device. Not very good for the end users to go, why is my application not working? Just make sure you only give it to people that it should work on. There's still some hardware manufacturers that do things stupidly and your application won't work on it anyways, but such is programming. So basics, we have the renderer. So this is actually in charge of rendering to the screen. So we'll handle the window resizing itself. It's an interface, not a base class. So Java, unlike C++, has the difference between interfaces and base classes. Base classes can define interfaces and give implementation. An interface is just purely, here's a list of functions to implement. So a renderer is just an interface. It can just, all it is this list of functions you implement. There is no underlying implementation from a base class. It's just implement these functions. I can call you like this. It's happy. You can implement as many interfaces as you want, but you can only derive from a singular base class. So renderer has the onDraw frame, has the surface changed, and the surface created. So onDraw frame, you can see a bunch of GL10 ignored. That's this deprecated code from the interface from when GLES 1.0 was on there. It's just ignored. It serves no purpose right now. Technically, you can use it to make sure you're running OpenGL 2, but there's really no purpose. There's no purpose for GL10 to still be there besides making everything work nicely and not changing the interface around. On draw frame, you draw everything you want there. So all your draw calls should be somehow correlated to draw frame. You call some function that draws your scene. That's happy. On surface changed, if the user rotates the device, that'll cause onStart to be called. Okay, rotate a device, destroy everything, and then call onStart again. So when you rotate the device, that's essentially restarting your application so you can recreate the GUI for the new landscape orientation. So there's an instance of where onStart will get called more than one time without exiting your application. I rotated my device. I am starting over again. On create will still only be called once, but you're basically just going, okay, you rotated, everything's destroyed as far as GUIs go. Recreate everything for landscape orientation. Not too useful here. Width and height swap, and you're pretty much done. On surface created is basically, hey, look, I created a surface. You can get the config of how the surface is set up, and you can go about creating your textures there. So you can load your textures there. Once that's called, you can start loading textures, and everything's nice and happy. Surface has been created. You have something to render on. Everything's nice and happy. So GL10 is ignored. So as you can see, GLES 2.0 as your packet, clear to color, and then clear to screen to that clear color. Nothing too complicated. Self-same as OpenGL on the desktop, except there's a GLES 2.0 in front of everything, as that's its package, which is essentially similar to a namespace in C or C++. So on surface created, set up your textures. If the EGL context is lost, so basically, if you want to recover resources, you would do it on here. When the context is lost, everything's freed for you. There's no on-device loss you have to really deal with compared to DirectX. It's just, oh, look, I'm going to get rid of this for you, and you need to go recreate it. So if you rotate your device, things like this can happen. You need to make sure you're recreating everything once the device is rotated and nice and steady and happy. So surface changed, width, height. All you really need to do is GLES 2, set the viewport to be that width and height. That's also called when the surface is created. So when your surface is first created, that's called, so you can set the viewport there. And it allows you to support all the devices, widths, and height you want. GL surface view, however, is an actual class. It has some base implementation to manage the threads, manage queuing things, and manage running the queued events on that thread. So you can do things like, hey, look, I want to load a texture, and I'm in my game logic thread. I can go, hey, post this to the GL graphics thread, tell it to run this task at some point, and eventually it'll run it, and you'll get your texture. So basically, you're telling the base class what context you're using. Then you're going to tell it that set EGL context client version. I want to use 1, 1.1, 2. So in this case, we're going to use client version 2, GS EL2. There's 3.0 should be coming out eventually. And then you want to tell it to set, you're going to tell it what renderer to use. In this case, we're going to use our own custom renderer. So we're just going to, in the constructor for our surface view, we're just going to tell it the GL render. Context as far as this goes is essentially what activity am I running from, what's the main, where am I coming from, what application am I running in, what's the activity currently, where am I going with that. We now have GL surface view, we have a renderer. So what we need to tell the Android application is, hey look, we have a view. This is something we can see. We need to tell it to actually make that to the user. So we're going to set the content view to our newly created MGL view. As you can see, I'm actually capturing a reference to that view. This is important because on pause and on resume, you want to tell that surface view you've paused and you resumed so it can properly handle resource allocation and making sure it's nice and clean and keeping itself tidy for the multi-application environment, which is Android. So now we basically have it set up to run a simple color. So not the most exciting of things. Yes, you're still open. So we're going to go ahead and launch this up on the emulator. We'll see a nice, pretty cleared screen. So this emulator that is running currently has GPU emulation turned on. It has hardware acceleration running. So if you've worked with Android before and saw the emulator being slow, you'll look up here and say, oh, look, this is fast. This is good. So look, now we have a nice screen clearing to gray. Yay, OpenGL is working. It's not white. It's just, we now have a nice gray screen. We're getting closer to having a nice working game. We have a screen. Yay, one step at a time. So not too much to that demo. Woo. So next big thing is 2D. A cleared screen is not a game make. What we need to do is make a game, actually, and start rendering something besides, hey, look, it's a screen, yay. So what we need to do is tell OpenGL to start rendering things, start rendering shapes and using shaders, as it dropped off fixed function pipeline. That doesn't exist anymore. You have to do everything manually. There is no ftransform, there is no GL matrix, there's no GL vertex. Everything's handled with what's called attribute arrays, which is a per vertex value, and it's just an array that you pass it to a shader. It gets one value at a time out of that array, whether you use indices or draw by elements. Indices will get the proper indexed value out of that attribute array. Just drawing it straight elements, it'll just go sequentially down, and each different call to an instance of the shader will give you a different value of your vertex array or your normal array. So if you worked on the desktop before, fixed function's entirely gone. It's not there anymore. Cleans up the code significantly to some extent, but sometimes can make it a little hard to get up and running. There's no built-in lighting or anything you can really use, but it does force you to learn how shaders are, and shaders are useful. So Android does give you a small matrix library for OpenGL. So A equals A concatenated with B is not safe, as it assumes that the result is not referencing either of the two inputs. More on that later. So there is some issues with that matrix library. So you probably want to make your own anyways, but it is there. Assets, there is a resource raw folder. So if we look at our source code hierarchy, we'll see resource. So we have drawable. So basically anything you want to draw, but not from OpenGL, your icons or etc., you can throw into drawable. High density, low density, medium density, extra high density. So high density pixel, low density, medium density, extra high density, this for different screens. So you'd have a higher resolution image here than the low density. So this is making sure that your application has graphics for every different screen resolution if you're not using OpenGL to render things. So your icon or something would have a different sized icon for each different type of screen device. So a little tiny phone would have a different icon than a tablet with a much larger screen. Makes sense. If you want things not to get changed, you can have the res. So you have assets or resolution. So you can either throw it in assets or create a folder called raw under RES. Android won't touch that. It won't manipulate it anyway. It won't compress it. It'll just be what you stick there. Assets, same thing. It'll be exactly what you put in there. No compression, no manipulation of your data. So if you want to make sure your data stays your data, either put it in assets or in the raw folder underneath the resources. I'm not going to do things fancy with stock. All the shaders are just going to be hard-coded strings. You can actually want to write an actual shader parser. So as far as compiling shaders go, exact same stuff as on the desktop. Create a shader, give it a source, and compile that. It's either GL vertex shader or fragment shader. So either something that works per pixel or something that works per vertex. Code is a sum string containing the entirety of your code. So unlike DirectX, you can't just say, here's an effect file, compile that. You have to actually parse it into some string somewhere and then give that to OpenGL, containing everything that is that code. Generally, you'd have one file for your vertex, one file for your fragment. Works out decently enough. Once you do this, you have to bind them to a program. At this point, you can use GL bind attribute location to get the attribute locations instead of using GL get attribute location later. You're basically saying, give me a position. It's going to work nicer that way, as you're guaranteed to have a position, as you're saying, hey, that position is now this. Lovely. Making the program, again, you want an integer to control everything's by handles. You're not using pointers. Same thing as C. So you're getting a handle to a program. You're going to attach your vertex shader and your fragment shader to that. So that then takes them into a single composition. This is used by use program and to uninstall, which basically means I'm no longer using the shader, just use program 0. That gets rid of it. So then your next render calls can use a different shader. Not too important when there's not fixed function floating around, as you're always going to be using a shader, so you're probably always going to be prefixing something if GL use shader. But if you want to uninstall it, GL use program 0 gets rid of it. Enough for saying is checking compile status of your shaders is very useful. Sometimes it's a bit hard to find this information. So what we want to do is we have an integer array, and we're going to create it of size 1. What we're going to do here is, and Java has not the concept of you controlling much of anything. So when you have a function, if it's an object, you're passing it by reference. If it's an integral value, it's by, if it's an integral type, it's by value. So it leads to an issue when we have something like GLGetShader IV. It wants to basically take a pointer and modify the value. So we can't pass integral values by anything besides copy. So it'll always be copied. So to actually do this and get around this, we create an array, which is essentially equivalent to a class and will be passed by reference of size 1. So we're creating an array of size 1 to basically pass a single integer down into GLGetShader IV to give us back the compiled flag. Weird little quirk of Java. It doesn't really give you control over how you want to pass data, so we make little workarounds like this. So a non-zero result indicates an error, at which point we can then make a string to get shader info and just give it the shader. That works a bit nicer than on desktop GL, as it's just one parameter and one output. It's like, hey, give me a string. Okay, there's no allocation of functionness there. You just get back the information. This allows you to print a logcat, which is the equivalent of the console or output window on Windows applications. This is a little window inside the bottom of the Eclipse IDE. That's nice. So probably should wrap all this up in a class, static functions, centralize all your checking so you don't have this everywhere. Just make one class with static functions, which is as close as you'll get to in just a namespace with pure global functions from C++, as everything has to be in a class. So a static class essentially a class that has nothing but static functions can kind of work like a namespace in C++, as it has no implementation. It's just functions. As close as you're going to get. So now we can compile shaders, link them, and make sure they're not erroneous in any manner. So in this case, we're going to render a square, not a triangle. So there are two means our data needs to be represented and to be usable. So in C and C++, you have the concept of a void pointer. It can point to anything. Java does not have that concept. So it has the concept of a buffer, which is then derived to be a float buffer, a double buffer, an unsigned short buffer. So whatever type of data you're using, you need a buffer of some variety for that data. And then you can pass that to an OpenGL call, as you can pass a reference to a base class can point to a derived class. So it's just using that instead of using void pointers, as pointers don't exist. There is no void pointer. Can't do it via void pointers. The other representation you'd have your data in is an actual float array. This you can actually manipulate a lot easier. This you can manipulate and go, okay, at index 0 caused this to happen, index 1 caused this to happen, index 2 caused this to happen. A buffer, you can place something at 1, you can place something at 2, you can place an entire float array in there. The buffers are pretty much just for packing your data and giving it to OpenGL. You're not really going to be manipulating your data directly in buffers, as it's not exactly friendly. So basically, in this instance, I'm using a float of values. I'm going to allocate 4 times float size, which is 4. There is no size of operator, so you just have to go floats are 4 and move on. So I just have some defined for float size to make myself feel happy about magic numbers in there. I'm using 4, so I'm using a x, y, z, and w because it's 4 times the size of floats. Or no, yeah. So let's allocate memory for that. And then I'm going to tell it to use the native order of the device. Then I'm going to move it into the float buffer. And I'm going to put my vertices there. And when you put something there, basically the vertices has a position of where it is currently. That's going to get shoved to the end when you put data in there. So you need to shove it back with just telling it go back to position 0 once you stick your data in there. So anytime you change your data around and reshoving back into buffer, make sure you're setting position back to starting, else it's going to be thinking you're somewhere in the middle of La La Land. So our actual shader code, as you can see, there's actually precision, medium precision floats. You actually have to tell it what type of precision you want on floats, and no longer just assumes. So you have to tell it what precision you're using on float. As you can see, I'm using attribute vec4 v position. This is that attribute array I was talking about before. So per each vertice, I get a different value of v position. So if I'm using indexed calls, it'll basically, if I'm on index 0, it'll give back me the 0th v position from the array. If I'm just going sequentially, it'll go 0, 1, etc. It'll just give you back each v position. It says in lieu of GL position, if you've used desktop OpenGL and it doesn't exist, fixed function is completely gone. Everything needs to be handled with vec4s. Newer versions of desktop OpenGL do use this, but if you're just taking CS300, you won't have used that to pass in positions or normals or pretty much most of anything. Still, you're still setting out GL position. This just tells it for this vertex, the final position is this. I'm just taking the position and then transforming it to projection space using the model view projection matrix. Yeah. And then in there, I'm just taking the frag color and setting it to red. So ftransform's gone, GL vertex is gone, fragment shaders require a precision specifier. Anything else that's fixed function, that's gone. If you do not make your own math library, if you use the Android OpenGL matrix, that has everything you're going to need. That allow you to set frustrum, set projection, allow you to multiply two matrices together, etc. All that functionality is there for you. However, let's say we have two matrices A and B. We want A to be the result of the multiplication between A and B. Matrix.multiply, matrix by matrix, takes a result, left-hand side and right-hand side. It assumes that left-hand side and it assumes that result is not pointing to either left-hand side or right-hand side. The result has to be some for float array somewhere. So all these are mentioned by float arrays. This actually can work out nicely. So your vertices or your indices has to be passed by buffers. Upper data such as a matrix can be passed just by a float array. This is never really going to be anything besides a float. It will always be a float. So let's assume it's going to be a float. You pass it by float array, so there is no doubly storing your data for matrices. That's only pretty much for your positions or your indices. You need to decide on what type you're storing it as and use the appropriate buffer to get that data there. For something like a matrix, That's never going to change. You're always going to be passing your MVP down as floats. So in this case, A equals A cross B has to become C is equal to A times B, and then copy C into A. If you write your own library, you can make these copies yourself. You can wrap up this library to make these copies. And if you make your own library, you just have control over everything, can add whatever features you want, and then reuse it on any project with Android. So probably a decent investment of your time to make a matrix library that you know is going to work correctly and not going to make you spend 3 weeks looking for a bug caused by assuming the result is not right-hand side or left-hand side. So, yeah. So that was the simple screen demo. So if we go ahead and run our thing, hey look, we have a cube. That's helpful. So if we rotate it, we have the model view projection in there. It'll get the on-surface changed. It'll update the viewport. It'll update the model view projection. And the cube will still look like a cube, but won't skew or stretch. It looks nice. After the presentation, you can come up and play around with this on the tablet up here. KDE's keyboard shortcuts conflict with the emulator's shortcuts, so I can't rotate the device on here. It just KDE takes preference. Bit annoying. So 2D, bit boring, right? So if we actually want to do something more fun, we can actually extend this to 3D and loading actual models. So here's a cube, slightly more advanced application. We're going to want to load an actual OBJ file in. So in this case, I'm just supporting the OBJ file format. It works, it's simple. As you can see, this is on mount SD cards. This is the SD card on the emulator. Earlier today, mounted an SD card, created it, moved files onto it. So if we go ahead and run load that, it's going to start loading. Nice little pop-up message. Progress bar, all fancy and happy. And then we have a 3D model loaded. A bit hard to tell it's 3D without lighting, but there's a model that was loaded in. As you can tell, the emulator didn't take too much of a slowdown loading a model with tens of thousands of vertices. Without hardware emulation, we would have been here all night waiting for this to load if it didn't crash. So hardware emulation makes this work about as fast or faster than this tablet up here. Hardware emulation, a very good thing. It's worth installing Linux to get that to work. Because there will be times you're trying to actually run this in some manner you're presenting. So further resources, developer.android.com, the main landing page for all of Google stuff. OpenGL tutorials, still on Google's website. I will go over OpenGL 2 or OpenGL 1. Android API documentation. So this will get you the actual parameters for the functions on how to use OpenGL. So if you want to go there, it'll go, okay, here's the function. It's going to return a string, and it's going to take the shader. If you want to figure out how to use it, you have to go to Cronus. This is documentation, and Nerman page. This is to figure out what that function does and how to use it. And then go back and compare it to the Android documentation and see how it differs, and then abstract away any weird Java issues or parameter differences to see what it actually does on Android. As all this basically says is, here's a function, what parameters it takes. This actually tells you what those parameters are and what they do. So combine your wits together, you should get by. And if you want to actually get a book, OpenGL 2.0 Programming Guide, there's a webpage for that. It has sample code for iOS and Android SDK. It's not for any specific platform. That works out nicely. Decent book. It's not going to go, here's how it's on Android, here's how it's on OpenGL. It's basically going to go over, here's the GeoSL stuff you need to know, here's all the graphic stuff, not necessarily the platform stuff. Any questions?